Swayam Prabha. Digital India. Educated India.
Hello and welcome. This is lecture number 17 of CAD. We continue with our discussion on Bezier segments and curves. In previous lectures, we have discussed Bezier segment design. We had also noted that if we change the position of any control point, we observe a global change in shape in a Bezier segment. Let's concentrate on shape change features today, and let's look at certain methods through which we can in some way introduce local shape changes in Bezier segments or minimize the global shape change. There are two such methods that we'll discuss today. One is based on the subdivision procedure. That is, we'll try to subdivide a Bezier segment into two segments, try to change the shape of one of them. In the second method, without changing the shape of a Bezier segment, we will try to raise the degree of a Bezier curve. In a sense, we'll try to increase the number of control points so that the shape change is at least minimized, even if it is global. Let's take a look at the first method, the subdivision procedure of a Bezier segment. It may be desired to trim a curve at the subdivision point, retaining only a part of the Bezier segment. Or one may subdivide a curve and design a segment separately without changing the shape of the other segment, and therefore gaining additional design flexibility. Subdivision involves partitioning a Bezier segment RU at some point U equals C. Note here that the value of C will be in between 0 and 1, and it is going to be a particular value. Well, subdivision involves partitioning a curve into two segments, each of which by itself is a Bezier segment of the same degree. So the problem now is a Bezier segment is given by, let's say, n plus 1 control points or data points or design points, b sub 0, b sub 1 up till b sub n. This Bezier segment needs to be subdivided at point u equals c. As I mentioned before, the value of c should be in between 0 and 1. We need to determine two new sets of control points, namely P0, P1 up till Pn. So this is the first set, and Q0, Q1 up till Qn. This is the second set, so that the Bezier segments span the original Bezier curve in the parameter range 0, U, C, and C, U, 1 respectively. So the essence now is to be able to identify two sets of control points, this one and this one, in a manner that a Bezier segment can be represented by two separate segments. And the original shape of the Bezier segment remains the same. Let's see how we can determine these control points. Let's say we have this control polyline. Well, you guessed it right. This is for a cubic Bezier segment. And let's say this is our Bezier segment. I plot a point for u equals c right here. And I would like to subdivide this segment at this point so that the two parts are this one and this one respectively. And these parts will be independent of each other. As I mentioned before, you as a designer might want to change the shape of this segment locally without changing the shape of this segment, or you might want to trim a Bezier curve at this point, retain maybe this segment and eliminate this segment, or vice versa. Anyhow, you have many design choices. So this is the first segment and this is the second segment. Let's try to sketch the control polyline for the first segment. And this one is for the second segment. Notice that the control polyline will change, but the Bezier segment will retain its shape. So the first control polyline is given by points p sub 0, p sub 1, so on and so forth, p sub n minus 1, and p sub n. And the second one is given by q sub 0, q sub 1, so on and so forth, up to qn. Notice two features here. One, that p sub n and q sub 0 are the same, and the last tangent or the last segment of the first polyline aligns with the first segment of the second polyline, in a sense that the slope here is the same. The same control point here and the same direction of slope here will maintain position and slope continuity at this point. The question now is how to determine these control points, P's and Q's. Well, let's first express the two curves which are identical for values of u in between 0 and 1. Okay, so the first segment r sub 1 will be expressed in terms of parameter u prime as summation I goes from 0 to n, the ith Bernstein polynomial of degree n, a function of u prime now, times the control points p sub I. And notice, or this Bezier segment will be the same as summation I goes from 0 to n, the ith Bernstein polynomial of a new parameter here, which is c times u prime, times the original design points that were specified by you. Here we have used the transformation u prime equals u over c. What does that mean? When u is equal to 0, u prime is equal to 0. And when u is equal to c, which will be the case for the first Bezier segment, rather the first divided or subdivided Bezier segment, u prime will be 1. Let's go back and try to understand this better. At this point, the parameters u and u prime will have the same value, 0. At this point, the original parameter u will have the value c, but the new parameter value u prime will have the value 1. due to that transformation. Now this expression is going to be true for all values of u prime in between 0 and 1. How do we extract conditions to obtain the new control points pi? Notice that pi will be n plus 1 in number, and so we will need n plus 1 such conditions. Well, to find the new control points p's, we use the fact that the curves n derivatives are identical at u or u prime is equal to 0. That would mean that the n derivatives of this segment and this segment, which are the same in shape, they will be equal at u or u prime equals 0. We have seen this relation before. The kth derivative of a Bezier segment, in this case r sub 1 as a function of u prime, is given by n times n minus 1 times up till n minus k plus 1 summation I going from 0 to n minus k, the ith Bernstein polynomial of degree n minus k as a function of u prime, times capital P sub I super k. This is equal to c raised to k times n minus 1 up till n minus k plus 1 summation I going from 0 to n minus k, b sub I n minus k function of c times u prime times capital D sub I k. What is capital P sub I k and what is capital D sub I k is something that you would know from previous lectures. Now, at u prime is equal to 0, this equation becomes n times n minus 1 times a few more terms, the last term in the multiplication being n minus k plus 1 times p sub 0 k is equal to c raised to k n times n minus 1, a few more terms, times n minus k plus 1 times d sub 0 super k. A note here. This is the kth derivative of this Bezier segment here. And this is the kth derivative of this Bezier segment here. And both these derivatives are with respect to u prime. Capital P sub I k, I'm giving you a clue here, will be in terms of the new control points P sub I, while capital D sub I super k will be in terms of the original data points V sub I. Well, coming back to this expression, we will have these two terms getting cancelled out, which would mean that P sub 0 k is equal to c raised to k times d sub 0 super k. In terms of the original data points pi, d sub I super j are defined such that d sub I super j is equal to d sub I plus 1 super j minus 1 minus d sub I super j minus 1, where the values of j are going from 1 to n and the values of I are going from 0 to n minus j, while d sub I super 0 is equal to b sub I, the original design points. This is, as you have guessed it right, a recursive relation. Likewise, capital P sub I super j are defined in terms of the new data points that we need to find. And P sub I super j is equal to P I plus 1 j minus 1 minus P I j minus 1. Again, j is going from 1 to n and I goes from 0 to n minus j. P sub I super 0 is equal to small p sub I. Now for k is equal to 0, the equation gives p sub 0 0 is equal to c raised to 0 times d sub 0 0, which means that the first new control point is the same as the first old control point. For k is equal to 1, p sub 0 super 1 is equal to c raised to 1, which is c, times d sub 0 super 1, which implies that small p1 minus small p0, the difference in between the first two new control points is equal to c times the difference between the first two old control points. We already know what p sub 0 is. We can find what p sub 1 is. And that is equal to b sub 0 times c b sub 1 minus b sub 0. For k equals 2, we have p sub 0 2 equals c squared d sub 0 2. This would mean that p2 minus 2p1 plus p0 is equal to c squared times b2 minus 2b1 plus b0. We can compute what p2 is, and that is c squared times b2 minus 2b1 plus b0 plus 2 times p1 minus p0. We can substitute for p1 and p0 from these expressions. And eventually, after some algebra, we can find p2 as b sub 0 times 1 minus c squared plus 2c times 1 minus c b1 plus c squared b2. Now this is interesting. Physically, if you notice, then p2 looks like it is a point on the Bezier segment, rather a point on the quadratic Bezier segment, defined by control points b sub 0, b sub 1, and b sub 2. Here c appears to be a parameter. Likewise, over here, p1 would be like a point on a Bezier segment of degree 1. And you can use this physical observation and extend it to get P3, P4, and so on and so forth. What we saw previously was a little involved algebra to compute the new control points for the first subdivided Bezier segment. We have an alternative, which is surely based on geometry. Now recall this tabular computation of intermediate de Castelnau points from the de Castelnau algorithm. If you recall, this column corresponds to the original data points that you as a designer would have specified. The first column here or the second column here rather, corresponds to stage 1 intermediate decasology points. These are stage 2 intermediate decasology points. If you keep going forward, you would eventually get to stage n decasology point, which would be a point on the nth degree Bezier curve for a given parameter value u. Now keep the expressions for p sub I in mind, and remember what I told you with regard to the observation. Now try to identify those p's in this converging triangle. You would notice that your first data point is actually p sub 0. Next, you would notice that stage 1 first intermediate decasology point is your point P1. Stage 2 first intermediate decasology point is the point P2. Likewise, the final point for a value of C now here. So remember that these intermediate decasology points are for u equals C. Stage n, which is the final point on the Bezier segment for u equals C, is our design point P sub n. What have we observed? Without going through painstaking algebra, we can geometrically identify what the new control points P sub 0, P sub 1, P sub 2 up to P sub n are for the first subdivided Bezier segment. And they correspond to the top edge of this triangle. Now, using the geometric information that we have here, can we guess without using the algebra what the new control points for the second subdivided Bezier segment would be? I'm just asking you to guess, so it can be wrong. My guess would be that this point B sub 0 super n will be Q0. This point here will be Q1, and if I keep going from right to left, this intermediate decasology point B sub n minus 2 super 2, which is the last point in stage 2 linear interpolation, this would be Q sub n minus 2. Likewise, the last point of stage 1 repeated linear interpolation, this intermediate decasology point will be Q sub n minus 1. And this one, of course, the last data point will be Q sub n. In summary, therefore, the top edge would represent the new control points for the first subdivided Bezier segment for u equals C. And this bottom edge here of this triangle will represent the control polyline for the second subdivided Bezier segment, again for u equals C. Notice that these are n plus 1 data points, and so the corresponding segment here will be of degree n. And likewise, these again are n plus 1 data points for which this segment as well will be of degree n. Let's try to investigate this story further geometrically. But before that, we try to summarize this observation mathematically. P sub k is equal to B sub 0 super k for values of k going from 0 to n, and Q sub n minus k is equal to B sub n minus k super k, again k going from 0 to n. Now let's try to see this geometrically. How subdivision and the de-Castelju algorithm are related. We start again with a cubic Bezier curve. We have this control polyline, and we start performing repeated linear interpolations. So this one is stage 1 repeated interpolation, and this one is the second stage repeated interpolation. The curve that I just sketched is the original Bezier curve. These are our original control points: V sub 0, V sub 1, V sub 2, and V sub 3. Stage 1 intermediate de-Castelju points: V01, V11, V21. Stage 2 intermediate de-Castelju points: V02, V12, and the final point for value of u again equals c, V03. You would have observed that this Bezier curve is tangent to the last segment here, joining V sub 02 and V sub 12. And also V03 would lie on the Bezier curve. I'm emphasizing these line segments, joining V sub 0, V01, V01, V02, and V02, V03. I'm also emphasizing, using a different color, these line segments: V03 to B12, B12 to B21, and B21 to B3. Segment is the first part of the Bezier curve, while this one here is the second part of the Bezier curve. The control polyline in blue are defined by the points P, P0, P1 up till Pn in general, and the control polyline in red are defined by points Q sub 0, Q sub 1 up till Qn. And from this figure, you would already know what the P's and the Q's are, even without going through the algebra. At this point, the value of u, I must emphasize again, equals c. I'm highlighting the control points P's and Q's. Before we go on to the next method, let me pose a few questions to you. Try to figure what will happen if I change the location of any of these points. I must tell you here that subdivision procedure essentially lets go of this original control polyline and replaces that with two sets of data points again, P0 to Pn and Q0 to Qn. As a designer, what would this mean? You would now be free to work with the data points on the control line in blue and the data points on the control line in red. In a sense, you can move any of these control points to wherever you want, or you can move any of these control points again to wherever you want. Now, if I move P1, which is identified by B sub 0 super 1, to let's say a different location here, which segment of the Bezier curve, the original Bezier curve, will change? Would it be this segment, or would it be this segment, or would it be both segments? Think about it for a little while. Or maybe, while you're thinking, I'll pose another question. What if I decide as a designer to move this point maybe to a different location here? Again, which one of these segments will change in shape? This one, or this one, or both? In a sense, what I'm trying to ask is, would you think now that after subdivision, or after subdividing the original Bezier curve into two parts, would I see a local change in shape? Okay, my answer to the first question: if I move this point to a different location, only this segment changes in shape. Would that be obvious? Answer to question 2. If I move this point to a different location, the segment on the right will change in shape, while the segment on the left will retain its shape. Only if I move this control point here, identified by P sub n or Q sub 0, because both these points are the same, I would witness the shape change in both segments, this one and this one. So in a way, would you agree with me that subdivision introduces local shape change features in the original Bezier segment? If I were you, I would say yes. Let's move on to the second method, degree elevation. The idea here is to improve flexibility in design by increasing the degree of the original Bezier segment, which results in the addition of a data point. The shape of the segment will, however, remain unaltered or unchanged. We all know this. A Bezier curve is defined by control points B sub 0, B sub 1, B sub n. Let's say these are n plus 1 control points here. Okay, and the problem is to find a new set of n plus 2 control points given by Q sub 0, Q sub 1 up till Qn plus 1, so that the original shape remains unchanged. The new Bezier curve is going to be given by summation I going from 0 to n plus 1, n plus 1 combination I times 1 minus u raised to n plus 1 minus I times u super I times qi. This is how a Bezier segment will be represented using new control points qi. You guessed this right. This is the ith Bunstein polynomial of degree n plus 1. And this entire Bezier segment will be the same as the original segment, because I have mentioned here before that the shape of the segment remains unchanged. The original segment, as you know, is given by I going from 0 to n combination I times 1 minus u raised to n minus I times u super I times the original integer upon bi. Now this expression is true for any and all values of u in between 0 and 1. Using this expression, can we determine what q sub I will be for values of I between 0 and n plus 1? Here, we need to do a little mathematical trick. Notice that this polynomial here is of degree n plus 1, while this polynomial here is of degree n. How do I make this polynomial of degree n plus 1? Intriguing, isn't it? What if I say that you multiply this expression by the term 1 minus u plus u? In a sense, you are multiplying this by 1, but it is the terms 1 minus u and u which will elevate the degree of this expression or of this Bezier curve by 1. This is precisely what I have just said. If I see one term in this expression, any term, then that is equal to 1 minus u plus u times n combination I, 1 minus u raised to n minus I times u raised to I times bi. Absorb this term into this to get nci 1 minus u raised to n minus I plus 1 times u raised to I times bi plus n combination I times 1 minus u raised to n minus I times u raised to I plus 1 times bi. All we need to do now is try to compare individual coefficients of the term 1 minus u raised to n minus I plus 1 times u raised to I. Well, even though I have not expressed the summation sign here explicitly, it is there. So what is the coefficient of 1 minus u raised to n plus 1 minus I times ui in this expression? That is q sub I times n plus 1 combination I. From here, it is n combination I times bi, which is this term here. And from here, it may not be apparent as of now, but if you try to change the index I to I minus 1, this will become I minus 1 plus 1, which is I, and this will become n minus I plus 1. So there we have this expression also contributing a term, and that term will be n combination I minus 1 times b I minus 1. You can work the algebra out. You can expand n plus 1 combination I in terms of the respective factorials, and you can rearrange the terms to eventually get q sub I equals 1 minus I over n plus 1, the entire thing times bi plus I over n plus 1 times b sub I minus 1. What do you notice here? qi is expressed as a linear interpolation between points bi and bi minus 1. Also notice that this term here, I over n plus 1, which is the same as this term, changes as we increase the index. from 0 to eventually n plus 1. So like in case of Bezier segments, in repeated linear interpolations, we had held the parameter value constant, if you recall the de Castaldi algorithm. In this case, if we perform a similar procedure, and if we consider this to be a parameter value, this would change and in fact increase as I increases. Again, this index I will go from 0 to n plus 1. Let's take an example. We are given data points A, B, C, and D. The two-dimensional coordinates are for A, 0, 0, for B, 1, 2, for C, 3, 2, and for D, 6 and minus 1. We raise the degree or we elevate the degree of this cubic Bezier segment to 4, 5, and so on and so forth. And we try to determine and show the new control points and therefore new control polylines. We have just seen this expression. All we need to do is plug in the values and get the QIs. For example, Q sub 0 is 1 minus 0 over 3 plus 1 times B0 plus 0 over 3 plus 1 times B sub minus 1. Now this is interesting. Although we do require the original data point with index minus 1, well, it is because this I is 0 that we don't actually need it. In a sense, Q sub 0 will be equal to the original data point, or the first data point, B00 in this case. Q sub 1, keep on increasing the index. This is 1 minus 1 over 3 plus 1 times B1 plus 1 over 3 plus 1 times B0, computed as 0.75 and 1.5 as the x and y coordinates. Q2 is equal to 1 minus 2 over 4 times B2 plus 2 over 4 times B1. The x and y coordinates are 2 and 2. For Q3, it's 1 minus 3 over 3 plus 1 times B3 plus 3 over 3 plus 1 times B2. Coordinates 3.75 and 1.25. Likewise, we can compute the final point, Q4. The coordinates are 6 and minus 1, which is the last point here. Let's take a look at this figure. The control polyline in blue is the original 4 data point polyline, for which this is a cubic curve. The control polyline in red here, which has this data point, this one, this one, this one, and this one, represented respectively by Q0, Q1, Q2, Q3, and Q4, represents the polyline for a degree 4 Bezier curve. And notice that the degree 4 Bezier curve would be the same in shape as a degree 3 Bezier curve. There's no shape change. Likewise, using these Qs, I can raise the degree of this Bezier curve by 1 again. I'll have 6 data points, and those data points will be shown by the control polyline in black here. 1, 2, 3, 4, 5, and 6. And I can keep on elevating the degree of this Bezier curve without changing its shape. So, from the design perspective, what is happening? I'm introducing additional data points or design points and retaining the shape of the curve. Try to compare two scenarios here. Had I worked with the polyline with 4 data points, the blue polyline here, and had I moved this point to a different location, would the change in the curve shape be significant compared to the following case that I'm talking about? The case where I move this point to maybe a different location. I would say that had I moved this point, the local change in shape over here would have been less compared to had I moved this point to a different location. Well, I had just said local change in shape. I know, and you also know, that the actual change in shape will be global. What I meant by local here was the change in shape in this region here, in the neighborhood of the data points that I have moved. Another point, if I keep on raising the degree of this Bezier curve, I can do it infinitely many times. As I keep on raising the degree of this Bezier segment, notice how the new control polylines become closer and closer to this Bezier curve. The blue one is a little far. The red one, with 1 degree higher, is a little close. The black one, with 2 degrees higher, as opposed to the blue control polyline, is even closer. And if I keep on raising the degree, I'll get closer and closer to this curve. Of course, again, without changing the shape of the original Bezier curve. In fact, this curve by itself would represent a control polyline constituted of many, many points, if you think about it from the perspective of degree elevation. In summary, as degree elevation is continuously performed, the control polyline approaches the Bezier curve.